Okay, hello everyone. Welcome to Being Patient Brain Talks. I'm Deborah Kahn, founder of Being Patient. Welcome to our community and our regular viewers. As you all know, I'm quite obsessed with the latest technology and how it relates to the brain. Virtual reality, we all know, is moving forward in the space of especially working with people with dementia. We've seen, really memories come back through VR, people relating to longer term situations. But this is really a very interesting study coming from UCLA, Dr. Mayank Mehta, who is really looking at virtual reality and what it means for memory. So welcome, Dr. Mehta, and it's great to see you.
Thank you. Good to see you, Deborah.
Okay, tell us a little bit, because as I said, we know that a lot of technology is really trying to figure out things we don't know about the brain. Specifically in your work at UCLA, what are you looking to discover?
Yeah, great question. So, as you know, I'm a professor in the Department of Physics. I did PhD in theoretical physics, how the universe began, the structure of space-time, and very mathematical stuff. And now I'm a professor not only in physics, but also in the Department of Neurology, as well as in the Department of Electrical and Computer Engineering. So why would I be studying the brain? Because physics and I don't know, electrical engineering don't seem to have anything to do with the brain. So the short answer is that a long time ago, people discovered that several of us who may have dementia or Alzheimer's, or even younger children which may have memory disorders or learning disabilities, it's not as if their eyes are not working. They can see quite well, most of them. Some of them have eye problems that are separate. They can hear quite well, but somehow something goes wrong where they're not able to learn and remember. Many of them can walk, they can talk, they can eat, they can take care of themselves, unless it's a very stage Alzheimer's, which we are going to talk about later. But otherwise, there are a large number of human beings which seem to be able to hear, see, walk, eat, do everything well. But there is this weird thing called forming a concept. For example, if there's an Alzheimer's patient, you can ask that person, especially the earlier stages when they're still talking, say, what did you have for lunch? And the patient will say, I had, I don't know, beans and potatoes. If there's a normal person, an Alzheimer's patient might struggle. Clearly, the patient ate the food, could recognize it was beans and potatoes, but somehow didn't remember. So this is called an episodic memory. There was a specific episode that happened, and that memory is somehow missing. So it's not like the sounds are missing, the lights are missing, ability to recognize is missing. Somehow these set of things, such as the smell of potatoes and the color of the beans and the taste I had and the movement I made, all that complicated thing put together didn't work together. So I got interested in that because amazing work done by a large number of scientists, neuroscientists, have figured out how this part of the brain, for example, responds to sight. And
Wait,
maybe
when you're
this
this
part
part of the brain, what specifically is this?
primary visual cortex at the back.
Yeah.
That was the Nobel Prize winning discovery in 1960s, to say that's what is really cares for vision. And then all the way here cares for decision making, and here
This is
cares for
frontal
touch.
cortex, right? The
Frontal cortex, and
yeah.
on the side you have the homunculus, you have the motor cortex, you have auditory cortex, and so on and so forth. So we know that quite well. And each of those parts of the brain, Deborah, is taking care of one thing. We know that quite well. And the question is, who is putting it all together? Who puts it all together? So we started with the hypothesis that maybe what goes wrong in these so many learning disorders, including a child that's sitting in a school, they can see the blackboard or the whiteboard, they can hear sounds, but they're not able to fit things together. From the sound and the eyes and the movement they made in writing and so on, maybe that's a problem. How does the brain do that? And then the next level of question was that at the end of the day, when I had an experience of beans and potatoes, I had a certain set of experiences. Each of them were very specific things, such a taste at a given moment. I cut the potato with a knife, but I don't remember all that. I have extracted out a concept called lunch of beans and potatoes. So that's a very sophisticated thing. It's not about perceiving the beans or potatoes. It's about putting those things together, abstracting them, and getting the gist of it to say that was lunch.
Okay.
How does the brain create such abstract ideas?
So I'm thinking you have actually sparked a lot of questions in my mind already. So wait, I want to slow down before we speed up. So when we're looking at Alzheimer's disease specifically, we know that short-term memories are what's difficult, right? What did you have
That's
for
right.
I don't remember. But then where were you born? Or tell me an experience
That's
in your
right.
childhood you remember. So
That's exactly right.
when we look at this, are we saying that the way that the brain brings it together, long-term is embedded, short-term is not? And so that ability to take a lot of these stimulus that make up learning, whether it's sight, smell, touch,
Right.
that part of the brain is not working as well?
That's right. So that's exactly right. So the problem is complex. So as you mentioned, very important point that Alzheimer's patients, their memories from the childhood and so on are fine. But the memories of just half an hour ago, they seem to be gone, which is the opposite of most of us. We may or may not remember things from our childhood as well, perhaps, or maybe better than Alzheimer's patient, but we will remember compared to them what happened just a few minutes ago much better. So people have been, yeah.
Yeah, so virtual reality, so creating a virtual reality, what does this enable us to learn about this process?
Right. So in order to do that, I want to first tell you a story. And the story is a very simple one, and it goes to the heart of the bigger problem that we are here to discuss, which is that human beings have been studying the brain for a long time, human brain or mouse brain or a rat brain and so on, and they have not been able to cure Alzheimer's. Why is that?
We still don't know a lot about the brain.
That's right. One possibility is that there is some unknown mystery about the brain that we don't know, and that's why we haven't cured Alzheimer's. But let me tell you a secret. Alzheimer's actually has been cured. There are at least 20 drugs that have cured Alzheimer's in mice. 20 drugs have cured Alzheimer's in mice. They failed in humans.
Well, wait, let me just clarify though. Most mouse studies do not translate into humans, correct?
In Alzheimer's. That's not true for Tylenol. That's not true for diabetes drug. That's not true for heart attack drugs. Lots of drugs. We test all the drugs in mice because unfortunately to measure whether the drug is doing the right thing or not, we have to do some invasive measurement of the heart or the brain, which we can't do in normal human. It causes damage. So we want to test for safety reasons, the effectiveness of therapy, first in animals so that it is working, it doesn't cause side effects, and then we want to test it in humans. And the weird thing is that Alzheimer's has been cured in mice by 20 drugs, not one or two. All of them fail. And it's such a big problem that major pharmaceutical companies like Pfizer have stopped doing research on Alzheimer's because they lost billions of dollars. The translation didn't work. So in my mind, there is a unique problem with learning and memory diseases, especially Alzheimer's, which is that the drugs work in mice, they don't work in human. And we can't directly go to human. God, heaven forbid, there's a nasty side effect and now the patient suffers even more. So the main challenge has been how to translate drugs from mice to humans. Now that immediately poses a question to you. How do I ask a mouse, hello, Mr. Mouse, what did you have for lunch today? How do I ask that right? I can't. So I can test if the mouse can see something or not. can hear something or not. I can test it rather easily. If it startles, moves or something, it's done. How do I ask a mouse, what did you have for lunch? How do I test episodic memory in a mouse? Now, I want to start with an ancient story which we humans forget. So if you don't mind, let me share the screen and then we can go from there. So that's a story. If you can see the screen. So let me read that out. So this is a classic story. This is an ancient Chinese painting that you can enjoy while you're reading this story. So there was this Zen master, and the Zen master and his student were walking by the river. And the Zen master said, look how happy the fish are in the pond because they are thrilled to watch the birds fly by. And the student was a smart one, say, hey, since you're not a fish, how do you know what makes fishes happy? Valid question. You see the relevance of what we are talking today? How do I know if the drug is curing a mouse? Because mouse can't tell us. Starts to get better. So the master said, since you are not I, how can you possibly know that I don't know what makes fish happy? And then the story goes on quite a bit, and I will not go through the whole thing. And it turns out this was done in roughly 476 BC. It's an ancient problem that we are dealing with, that if we want to test drugs in animals, especially drugs that require a cognitive report, how are we going to do that? So let's get into that a little bit. How do I test memory? So here is your eye. Let's say we are thinking memories only through eyes, then we are going to worry about ears and touch and so on. And then that information from the eye goes to all these complicated circuits. This is the back of the brain, the primary visual cortex, and then there are a huge number of stations in between. This is an old picture. There are many more stations in between. Each one does something funky. We don't have time to talk about any of this. And all the way at the other end is this circuit called hippocampus. That's at the opposite end. This thing, many of you, the listeners who are aware of the artificial intelligence, looks like a deep network. This is the input layer. There are a whole bunch of intermediate processing layers, and this is the output layer. And lo and behold, the output layer does abstraction, generalization, memory, and so on. Sounds like it's a real deal. But funny thing, and that's called hippocampus. That's where Alzheimer's begins. Hippocampus not only is the place where Alzheimer's begins, it's also the place where there is autism, Alzheimer's disease-related dementia, depression, PTSD, schizophrenia, psychosis, epilepsy, and many more. So why is it then that that tiny structure has all these diseases? If you take any other random brain structure equally big, it doesn't have these diseases. So why so many diseases are sitting around in that tiny structure? None of them are curable, not just Alzheimer's. So people realize that this is a challenge. And how do you ask a mouse to say what was an episode? People thought, well, since we can't have a conversation, and since Alzheimer's patients often get lost in space as well, they forget where their home is, they get down at the wrong stop, they thought maybe we can probe the mouse's ability to know where I am. Rather than, am I seeing blue or am I seeing red? Where am I? So that experiment got the Nobel Prize, and I'm going to show you the data. Is going to be a mouse running in the real world right now. We're going to listen to one neuron. So there's a top-down view of a maze. It's a square maze, and there's a mouse that we are rendering the mouse's path, and the crackle is a spike of one neuron. So what you note, we are going to speed this up soon enough. And what you notice, as the mouse is moving in this maze, as you can see, that neuron, even though mouse, so this is half an hour worth of data, mouse was eating, drinking, scratching himself, checking out the walls, God knows whatever else mice do, that neuron was active only here and nowhere else. And other neuron will be active here, here, and so on. And as a result, this pioneering discovery led to the Nobel Prize in 2014, that neurons in hippocampus contain a map of the world. A GPS system of the brain is what hippocampus is called. Now, here is a problem of why that didn't work. You wanted to ask a question.
No, this is fascinating. Okay, come to the problem. I do have a question, but go ahead.
There it is. So now there is a problem with this way of assaying what's happening in the brain without asking language-based question of what did you have for lunch? Space. So in rodents, the hippocampal neurons, according to 30, 40 years of classic research, are supposed to represent abstract location of the animal, not any specific stimuli. Those neurons don't seem to care for what the mouse is looking at a given moment. Is the mouse looking at the door or something, or the window, or the food? It's supposed to be abstract. They are not supposed to be response to any sensory stimulus. It's just an abstraction. And there is no really relationship of that with a specific episode because mouse just walking around. Now, if you compare that with the measurement of these neurons in primates, now note that doing such experiments in primates is really hard. You don't want to do experiments in primates unless it is really, really necessary. These are invasive experiments. You would rather do that in mice and rather not even in mice, but so heroic efforts by people found that actually when they measured the activity of neurons, like the same experiment I did in primates when they're walking around, there is no spatial selectivity. Now we have a problem because if somebody develops an Alzheimer's drug, they want to test whether the drug is curing the Alzheimer's at the cognitive level in the mouse's brain or not. They check the mouse's ability to navigate in the world. That's the unique assay. But primate neurons don't seem to have any map of the world. Even worse, those neurons seem to care for what the primate is looking at, as well as a handful of studies in human. Mouse neurons don't seem to care for what it's looking at. We can show that the hippocampal neurons in primates actually respond to specific images, such as a famous actor or actresses. They recall it because they know those famous people. So that doesn't fit. And human hippocampus has strong episodic memory in several Alzheimer's patients. They're quite okay navigating within their home. It's their episodic memories that's damaged. So now we have identified the main problem, potentially the source why the drugs are not getting translated between rodents and humans is that the assay for testing mice to say run around in a maze and find the reward or something, that assay is not working in humans and rodents.
Okay, can you go back to the mouse? Because I'm a little bit confused about that pattern.
Yeah.
The pattern that we are witnessing in this video is that when it lights up, that's because the neurons are actually firing and there's something that it's something that they're responding to with the brain. So they're learning something at these darker points.
Hang on. We don't know any of that.
We don't know that.
All that we know, yeah, good point. All that we know is that this neuron fires only here. This is just one neuron.
And these are normal mice. These are not Alzheimer's.
Normal mice.
Normal.
That's exactly
Okay.
right. They don't have Alzheimer's. The normal mice, this is the best that the brain could do, hippocampus could do. That's the Nobel Prize winning discovery that one neuron fires only here, nowhere else. And if I had shown you the data of not just one, but 20, 30 neurons, another neuron will be active here, third active here, fourth here, and so on. And by looking at the pattern of activity of just 100 neurons, I could read off the mouse's brain and tell you what the mouse, where the mouse is without looking at the mouse.
Wait, so the darker imaging represents exactly what within the mouse brain?
It's a spike. So every neuron, whenever it's activated, it fires a spike.
Okay.
And that's what you heard. So if we start this once again, when the mouse walks, we're showing you where it walks. The mouse may not be leaving a scent trail. Maybe he does. We don't care for that right now. So you'll hear a crackle. That's the activity of one neuron. You heard that? That's a spike by one neuron was active only there. And notice that neuron, once again, when the rat mouse went in that region, fired, the mouse goes everywhere else, the neuron doesn't care. This is a phenomenal discovery that this neuron, 1 out of a billion, seems to be active only when the mouse is here and not anywhere else. And a similar pattern, but different place is true for different neurons.
So, so when you are saying your hypothesis is that we are aiming the drugs at the wrong what?
Assay. So when people do some Alzheimer's drug development, how do they test it? To say, all right, I'm going to develop a drug and then check the mouse's ability to navigate in a maze. Sometimes they even measure the neural responsive, but otherwise they simply measure the mouse's ability to find its way in the world, in a real maze world. Now, the problem is that such spatial selectivity is not found in the human hippocampus. So, potential, and you can say, well, maybe human hippocampus is doing something else. When human beings walk around, the neurons actually care for what the human being is looking at, which seems to be natural. But on the other hand, people think the mouse hippocampal neurons don't care for what the mouse is looking at. So it's all kind of going in the opposite direction. One is going to the left, another is going to the right. The two don't seem to match pretty much 100%. So that's where we got involved, and virtual reality is the solution.
Okay, so why is virtual reality the solution?
Very good question. So let's imagine that I'm a mouse. First of all, let's imagine I'm a human and I'm walking around in this room as I'm standing right now. My head is about a meter plus from the ground. I don't know what's exactly at my feet. I certainly can't smell my feet, heaven forbid, or anything near my feet. Now, let's imagine there is a mouse that's running on the maze. And let's imagine, I don't know, that's a maze. And that's where the mouse is running.
Wait, hang on. Should we stop sharing, Dr. Mehta,
Sure.
for now?
Sure, yeah.
Yeah. Okay. All right, go ahead.
So when the mouse is running, its head is like this. Its nose is right next to the ground. It has phenomenal sense of smell. People use mice and rats to even sniff out landmines half a meter below the ground. The nose is right here. They have whiskers. We don't have whiskers. The whiskers are highly sensitive. They are touching the ground.
Sorry. Yeah.
The eyes are next to the ground. The ears are next to the ground. And the vision is really not as great. Sometimes they are nocturnal and they don't see far away. It's like me walking here and looking up there. So basically, our hypothesis has been that when the mouse explores any space, because the mouse is ground dwelling, its experience is completely different than human experience of where you are. Human experience of where I am is largely based on vision, maybe a little bit based on sound. Occasionally, I will use the smell to say, oh yeah, that smells like bacon, or that must be kitchen or something. But most sighted human beings navigate using vision. Mice, on the other hand, they are constantly experiencing smell, touch, eyes, everything is on the ground. So our hypothesis was that the major differences between mice and human are because they're having totally different experiences. Even though both of them are in space, their experiences are completely different, and hippocampus is getting completely different experiences. So the question, if the hypothesis is true, I should be able to give either the human being the experience of a mouse, which means an Alzheimer's patient comes to the clinic, has to get down on all fours and walk around with their nose to the ground. Not really practical.
No.
Or I have to make the mice walk a meter above the ground. That's also not practical. So how do I make mice navigate only using vision? That's where came virtual reality. So if you wish, I can share the screen once again, and then you will see the results of that. So then we decided, as I mentioned, if you can see this, so we built this virtual reality system. Now, this is a unique virtual reality system. It's not stressful. We know that many tests of Alzheimer's disease, such as mice swimming in a tank of cold water, they are highly stressful. This is non-stressful. The mouse wears a little jacket. You will soon see the picture of the mouse in the virtual reality. He stands on this giant floating ball that's floating on the air. He wears a little tuxedo. It's not stressful. These microcontrollers and sensors pick up the movement of the ball that goes to the VR engine, goes to this tiny pico projector above his head. The room is fairly dim because these are nocturnal creatures. They don't like very bright lights, unlike us who love it. and it sends the image all around the mouse, including under his feet. That's very crucial. If you have ever put on the standard VR goggles, you find somewhat unnerving experience that you cannot see your hands or feet, which you're always so used to. In this VR, mouse can see its paws, can see its own shadow, and I'll show the images. So now the mouse has to navigate in this virtual world only using vision and maybe sound, but the smells and so on, irrelevant. Scent marks have become irrelevant. It's their positive memories. If he goes to the right place in VR, it gets a little bit of soda. Just like if I go to this kitchen, I get a drink of soda or water. You can do many, many trials, and we can standardize across labs. Can the test done in Boston versus tested in Los Angeles, in summer versus winter, the conditions are the same. And one can now use humans and rodents in the same condition. Because I can bring a human being, this VR is designed in such a way that this whole shell, one can remove the giant ball and the whole shell sits around the patient's head. The patient is seated comfortably in a chair. So a direct translation of the exact test. Whether a mouse or a human, both are seated in one place and they have to form a map of space. Can, first of all, mice do this task? That is the first question. Maybe just like mice don't care for television, they won't care for virtual reality either. So let me show you what the mice do. And this is the biggest thing. And so here's now the webcam, which is outside the VR setup. And it looks like the mouse is going somewhere, but he's just held in one place. These virtual chandeliers are appearing. And when he goes underneath it, he gets a bit of sugar reward. Watch his head, looking up and down at the pillar, saying, is he coming? Even though there is nothing above him. He's forming a map of space. Now, trial number 2 or 3, the pillar is behind him. Watch what he does, is to figure out where the reward is. Goes to the edge of the table, figures out that that's the ground, because the ground moves at a different speed than the top, turns away. And you can see, once again, I'll do one more demo. These are lots of papers we published to show that they are doing this task happily. They run around, they terminate the task when they want, they can slip out and end the thing. Watch his head now. Now he reaches the edge of the table, turns away, instead of going all the way, find the reward. In the final trial, I won't spoil it for you, watch what he does. So we have placed the pillar right next to the edge. Right there is the edge of the table. We have put him at the edge, he doesn't want to be there. He's not going to fall off any such thing. He tries to go back, then runs away. So mice actually interacts, buy into this virtual reality as if it's real. He doesn't want to fall off, even though he never fell off the table, because there's nothing to fall. So then we measured the neural responses in the brain from lots of neurons, and we had brilliant set of people in the lab to figure out what the neurons were doing. To make sense of the neural activity, we had to use a whole bunch of mathematics. I'd love to tell you what that math is, but
oh my gosh,
not today.
That makes me want to run the other way.
Don't worry. And when we did that, we found this amazing result. This is the trajectory of the rat in the real world, thin blue line, and the blue dots are, this is a different neuron than the one I showed you, which is the neuron's activity is very precise. It fires only here, nowhere else. This is the same neuron that is now active in virtual reality, and you can see it's a spaghetti. The neuron doesn't care at all where the mouse is. So that didn't go too well, but that starts to remind you of the observation I told you that in the primate brain or the humans which are walking around, there is no spatial selectivity. So these neurons, mice, hippocampal neurons, don't seem to care with pure vision. So that starts to match primate. So hippocampal neurons show place cells in the real world to generate a cognitive map, which is a Nobel Prize winning discovery that we have all been using to test the effectiveness of the Alzheimer's drugs. But in virtual reality, even in normal mice, there is no spatial map. So improving the spatial map is a moot point. But then we go slightly further. Then we look at the activity of these neurons as a function of the mouse's head direction. And this neuron likes to fire maximally when the mouse is looking in this direction of the maze, doesn't fire at all in the other direction, which too resembles what happens in the human brain, as well as primate brains. So when people did this experiment, and the primate was walking around in a room, but its head was again 50 centimeters from the ground, doesn't have whiskers and so on, they found spatially selective, position selective neurons, only 5%, close to chance level, just like what we see in mice. And the number of neurons that cared for what the primate is looking at was 3 times as much, just like what we found. So we conclude from this that rodents running around in virtual reality, where only vision tells them where they are, their hippocampal responses and the hippocampal function resembles very closely, in a very high degree of accuracy, how human hippocampus or a primate hippocampus behaves in the real world. Why that switch between real and virtual world? Because the real world in human, whether something is on the ground under the feet or not, makes very little difference to us unless it's very, very overpowering. For mice in the real world, the ground on the stuff on the ground is the most powerful stimulus. When they go to VR and this remote, mice start to look like humans. So we believe that the right way to test any drugs in mice, so somebody has a brand new drug and say, I want to know if this drug is likely to cure Alzheimer's or not in humans, not just in rats, whether this drug will work in humans. You need to look at the hippocampal direction selectivity in virtual reality and a couple of other things that I can share with you if there is time. We have written lots of papers, including this one where we showed how neuroplasticity markers can be actually remarkably uncovered in VR, and all kinds of episodic memory can be uncovered, but that's the punchline.
So how would this, so you are suggesting that in order to test drug therapies that are coming to the market, you need this type of environment with virtual reality to understand the efficacy in humans?
Exactly. You need to test mice in the same conditions as humans. Humans are walking around in the world, forming memories largely through vision, conversation too, but we can't have a conversation with mice, so let's leave that aside. When humans form maps of the world, it's based on vision. We need to take out all those other things, such as smells and textures and negative experience and all that, make a positive experience, and then the hippocampal dynamics across, hundreds and thousands of neurons that we measured very closely captures this. So that's virtual reality is a solid platform. So I can conclude from this, if you wish, to say billions of dollars are lost because many drugs for memory disorders, example Alzheimer's, work in mice but fail in humans. This is because mice are tested differently. For example, to remove smells, they toss the mouse in a cold tank of water. Now, you literally threw the baby with the bath water because cold tank of water is scary. And we can't throw Alzheimer's patient in a cold tank of water to see if they can navigate. Can't do that. And human beings form memories with positive things. So rodents in the real world versus humans in virtual reality. If you look at the task is aversive, the standard task that pharmaceutical companies use, which is this one. This is a negative task. Human beings usually walk around for positive reason unless there's a tiger chasing them, which is kind of rare. Rodents rely on whiskers and smell. Humans rely on vision and sound. Neurons care in rodents for position. No position selective in humans. Visual stimuli elicit direct response or no response in rodents, but the response, clear responses in humans. Spatial maps in rodents are present at birth. Episodic memories are formed in adults as a grown person. We are not born with it. And brain generates, in addition to that, we are now getting into something more interesting, that when rodents are walking around, the brain generates a new rhythm, which we can't perceive. And that rhythm is highly beneficial for neuroplasticity and learning, which is an 8 hertz rhythm. But in humans, the rhythm is a different frequency, half that of 8 hertz. So these are well-established problems for the last 40 years. And what
So,
we managed, yeah,
right. No, so to conclude, just to put this into perspective, what you are saying is virtual reality can mimic human experience in rodents so that we cancel the
exactly,
stimuli of smell and whatnot,
exactly.
being so close to the ground. And what this means is, and we already know that when you do that, the neurons travel differently. When you mimic with virtual reality in mice, the
That's
neurons are
right.
traveling differently than they would in.
Exactly.
Has any of this been tested to give us insight on the loss of memory rather than taking normal norms? I mean, do
That's
we
right.
know
So that I'm
deficiencies?
going to come to that. If I have, I don't know how much time we are left with, but
We,
I'm going to come to that.
okay, go ahead.
So
We'll give you the-
very good. So let's finish that. So if we have virtual reality, now we have direct the same test for rodents and humans, just vision and just virtual, not going anywhere. And the mice are sitting there just like that. And now in rodents in VR, we have positive memories, just like human patients. Your rodents in VR rely only on vision and sound, just like humans. Those neurons, when you look at the biomarkers, they do show no position selectivity like primates. They, on the contrast, show clear visual evoke responses, just like primates. And memories are formed in adults, and the brain remarkably generates a new rhythm, which is not seen in rodents before, but is common in primates, which is exactly the same frequency. So not
Okay, so
just,
this is, I think this question is relevant too, that, and this is really
yeah,
interesting. So we have a question from our audience saying that, great talk. It seems that you can only focus on the visual stimuli by using VR. However, isn't the VR only good for testing spatial memory, but not episodic memory?
great question. I'm going to come to that in a second. We're going to come to episodic memory in a second. But let me first take care of the spatial memory, since that's the bread and butter of vast majority of pharmaceutical companies. So essentially, based on this, we can conclude for the spatial memory part that several neuromarkers of memory agree fully between humans and rodents in VR, not just stimuli, but even biomarkers. And hence, this particular kind of virtual reality has lots of nice bells and whistles that I didn't go into, is ideal for developing therapies so that phase 1 therapy, you can directly rule out a drug. People are more than pharmaceutical companies. If they like to use the water maze, they can do that as well. They can just add this extra technique, which costs peanuts compared to phase 3 trial, which is, runs into tens, if not hundreds of millions. So that can save a lot of time. It can be done at low cost and at scale. Now, that's the main point. And we have filed, full disclosure, we have filed for a patent, which is approved. So we want to partner with pharmaceutical companies, and we want people to know this. We want people to use this so that we can accelerate drug discovery rather than getting lost in this translation. Now, the question about episodic memory, as well as question about can we go beyond this? And I touched upon that a little bit here. So what I'm going to tell you next is something even more surprising, which is virtual reality, we hypothesize, is actually potentially a way to treat Alzheimer's or many memory disorders. Sounds wild. What the hell is that all about? Let's get started. So we notice first time, for example, here is a certain pattern. We let the rat run around in the real world. RW stands for real world, and each of these ellipses is a different neuron. What the X and Y axes are, don't worry about it, some
Is this in
microvolts and so on.
humans or mice? Sorry.
Mice, this is
Mice.
all
Okay.
mice. We cannot really do that in human unless they already have brain damage. Only under those conditions we can put electrodes in human brain. So right now it's just normal, healthy mice.
Okay.
They have a certain number of neurons our electrodes can pick up. Now, it is well known that if you measure the activity in a mouse which has Alzheimer's, Then in the very early stages of Alzheimer's, hippocampal neurons have hyperactivity. The neurons become too active. That hyperactivity of neuron eventually starts to cause cell death, bigger brain damage, and then the A beta and tau protein starts to travel through synapses and so on. So we thought, what if we can shut down the activity of hippocampal neurons, just make them a little less active? Because these are all the neurons active, can I shut them down? Now, it turns out I can give the animal some drug which can shut down the neural activity, but that drug will go also to the neurons in my heart, and my heart will start to shut down. That's not a good idea. You don't want to shut down the breathing and the heart. So can I selectively shut down the hippocampal neurons by some magical technique? Here is that magical technique. When the same mouse was running in virtual reality, 60%, look at this neuron was robustly active here, it's gone. That ellipse is missing. That neuron right there, that ellipse is missing. This small one right there is present. This big ellipse right here, gone. So across the board, we were very surprised by this, that when these mice were running in this stress-free virtual reality, 60% shutdown of hippocampal activity occurred. Whenever the mice were running in.
That's not a good thing, is it?
We don't know that. We don't know if it is a good thing, if it's a bad thing, or if it doesn't make any difference at all. But what I can imagine is that if under some diseases, hippocampus is hyperactive, and we can tone down the hyperactivity, such as early stage Alzheimer's when there is hyperactivity, or epilepsy, when there is a temporal lobe epilepsy, when there is hyperactivity, potentially virtual reality therapy, at least during the therapy, the hyperactivity can be reduced. Now you may ask, okay, even if we can reduce the activity during the therapy, what are the odds that the therapy will continue when the patient leaves the virtual reality? Now, I must say that this is one particular kind of VR where this happens. There are many kinds of VR. This is a very unique one, as I told you, where you can see your hands and feet. So this is not a blanket statement about all the VRs, but with this VR, this is rock solid.
Okay,
So
this is kind of counterintuitive to what I've previously thought, which is, when we exercise, we're encouraging more activity in the hippocampus. So I've been told.
That's right.
So why would less, I know you said we don't really know, but what is the hypothesis around less neuron firing in the hippocampus a good thing? Like, what do we know about overactivity being a bad thing, I guess is the right way.
That's right. So this is something that I went through very quickly. That in several diseases, for all kinds of reasons that we didn't get into, for all kinds of reasons, neurons are hyperactive, they're overactive. And that overactivity of neurons is toxic. It starts to kill the neurons. It's called excitotoxicity. Overexcitation starts to kill neurons. So it's true that we want neurons to be active, use it or lose it, but there is a sweet spot. Just like salt is good and carbohydrates are good and fat is good, but if you take too much of any of those, it can kill you. Same thing is true here. You want some optimal level. So right now we have a technique by which we can shut down the activity in this neuron on command by 60%. We want to find out what are the long-term consequences for the brain health of this technique. Maybe it is good for Alzheimer's patients, maybe it is good for epilepsy patients, but maybe it is horrible for somebody who has depression. I don't know. And what we want to do is to find out. Right now, the average age of a VR user across the world is 14 years. Is this good for children? Is this good for adults? Maybe this is good for really old adults, but this is bad for children. I don't know. I'm not trying to say that this is a fantastic cure-all and everybody should start popping their heads in VR. All I'm saying is this is remarkable Nobody expected this. We now have a tool by which we can shut down neural activity. We are working on a new kind of VR where we can, instead of shutting down activity, we can also bump up the activity. And we have ideas how we can do that. So we now have through VR. Sorry,
So
let me
that was my question. Like, okay, so if we don't know how little or how much, maybe there's deficiencies where people need more neural activity, right?
That's
And
right.
are there, I mean, we define neuroplasticity by the way the neurons travel within the brain, and changing that pattern, which we know learning a musical instrument or learning a new language, we're changing the patterns
That's right.
of how the neurons are firing off. But
Yeah.
I guess my question is, just because we're learning new things doesn't mean we're generating more neural activity. It could mean we're just changing the patterns of that activity. Is that right?
No. Let me paraphrase it a little bit. I'm not saying that doing the VR is good necessarily. Once again, let me emphasize. I'm
We
not
just don't
saying
know.
that this pattern we are seeing in VR is good for everybody. I have no evidence whether this is good or bad or completely benign. We want to find out. But all I'm saying is that we have now a solid scientific way of shutting down neural activity. And now we can study the effects on Alzheimer's patients. Our hypothesis is that this will be good in the early stage of Alzheimer's as a therapy. This will be good to suppress epileptic seizures, potentially. We want to test it. But because now we have a tool, that tool shuts down hippocampal activity, but doesn't shut down the heart and the lungs and the stomach and the vision and so on, other things are remaining intact. So
Okay.
it's simply an additional thing.
Bringing, and that, I get that, and I hope we will learn more with VR, because it's a less invasive way, right, of
That's right.
studying brain pattern. But what about the spatial versus episodic? What do
Very
we
good.
know? Yeah.
So let me come to that. Let me see if I can go to that directly versus I come back to something else. Screen
Because
sharing.
in the
Yes.
beginning, we were talking about how episodic memory is impacted with people who have dementia, right? So
That's right.
they
So
might not remember what they had for lunch,
that's right.
but they will remember
That's
something
right.
from childhood, right?
So let's take a look at two things that we discovered. One of them is readily available. Other I can share with you a little later. So now that's a paper that came out in Nature just 2 years ago. So we wanted to see if there is an episodic learning signature in this mouse brain, and there is signature for certain episodes. So how do I define an episode, first of all? And what has episode got to do with space? Now, several people have hypothesized. So here's the task. So instead of just going underneath a pillar, the task is much harder. And I can show you videos and so on, but those are available online, so you can take a look. So the task is this. There's a big circular platform on which the mouse has to run around. There are walls in the virtual reality, have prominent cues, but there is no pillar telling the mouse where the reward is. It has to find out just by trial and error. And just for demonstration purpose, I'm telling you that the reward is here. If the mouse goes here, it gets a very solid reward. And then as soon as it gets the reward, it gets teleported to a random place. So let's say the mouse is released from here, it has to go here, released from here, it has to go there. So regardless of whether the mouse starts from north, east, south, or west, it has to reach at that spot to get a reward. So one can imagine that there are 4 different episodes that the mouse has to learn to solve this maze. That A, I started from the west and I went here. B, I started from south and I went here. C, from east and I went here. D, I went from north and I went here. No matter where I started, I had these 4 episodes of getting the reward. Can we now see signatures of neuroplasticity in that simple-minded episode that people have defined for the longest time? And then in a few seconds, I'll tell you completely, purely episode, not even space. What we find is that actually mouse's behavior improves. So this is the behavior of the mouse. These are the trajectories of the mouse's path. in the first 30 trials, you can see the mouse doesn't make a direct beeline to the reward, kind of gets lost a little. In the next 30 trials, you can see the paths are straight, it goes there directly. So there you can see there is signature of learning right within this task. And what you now see is the neural activity. You can see the neural activity level was 1.4, and within 30 trials, it increased by 60% in this virtual reality. So now we have a biomarker of neuroplasticity, neural activity is increasing. Even though overall neural activity has been reduced, the neural activity selective for this memory has increased. And these are more complicated things, but the bottom line is the neurons also, the episode, actually, this is kind of buried here. The episode is made up of, to say, I started from the west wall, I traveled 1.5 meters to go east in the northeast direction, and then I got a reward. So the episode is made up of 3 chunks.
Yeah.
I started from the west wall, I went in the direction of east, and at 1.5 meters, I got a reward. And these neurons actually respond to all 3 of them. And all these responses are highly plastic.
So
So
we
that's
know the training with episodic memory, the actual neural activity increases.
Exactly. And actually, neural activity starts to change before the behavior changes right there. So the changes in neural activity, the plasticity of neural activity starts to predict behavior, which is what you should expect. So it's a very strict controlled study that does that. And then if you wish, I can go to the final thing, which is, well, before I go to the final thing, I don't know which one I should cover first or second. I want to go to purely episodic memory, which has nothing to do with space. And I also want to go to how VR can generate beneficial brain rhythms. So which one?
So
do you want
I
to
think
cover
let's
first?
bring it back to what's useful to people, because this is highly technically scientific.
That's right.
And so
I know the question was episodic memory, so that's the simplest version.
okay, let's go to what this means to people, because I also I want to end, and we're going quite, we're covering a lot. So what I really want to talk about for the next few minutes that we have left is, what is it, what does this mean? What do we know about VR? And this might not touch exactly your research, but what do we know about VR and brain, either brain health or improving memory in a disease state? Have we linked the two together? Do we have enough data to understand? Because you're certainly proving within mice, you can measure patterns of neurons, but what do we know about humans in terms of memory?
That's right. So clearly, we are now, again, the answer is complex, and that's just the way it is. There is no such thing as VR. There are many types of VR. There are certain kinds of VR that make people nauseous. Some people feel nauseous, some people feel dizzy, people feel weird that they can't see their hands and feet. We got to remove those things, because even if VR experience might be beneficial, these things could be causing other things why the benefits don't show up. So the first thing, before I answer the question, whether the VR experience is better for certain aspects of cognition or not, we want to start with the kind of VR where these unwanted effects are removed. Now, having said that, there is fair amount of evidence that a VR experience is quite compelling at the cognitive level. This is not at the level of, at a subjective level. Like if you do a VR experience, that's far more memorable than an experience that you have in the real watching television, for example. So why is that? Is it just because it's a surround screen? Well, you can have a big giant surround screen TV and it still won't be as immersive as a VR experience. Why is that? That's what our research has gotten down to. And the main point there is that unlike a television that doesn't react to every movement of your body, VR does. You can simply move your head a little bit here and there and the scene changes zoop, like that. Now, it turns out that there is a solid relationship, a complicated relationship a map that is stored in your body or in your brain. Say, this is what I did, and this was the visual scene change was the result of my action. Very complicated, right? As I started from saying that Alzheimer's patients have problem remembering events rather than particular sensation. So let's do this thought experiment right now. You can simply sit back and move your head forward. And when you do that, the entire room's image will come towards you. You find that's perfectly normal. But let's do the opposite experiment. You are sitting there and the entire room came towards you. In a blink of an eye, you're going to duck. You're going to freak out. Or the opposite, that when you move your head, the room doesn't move. The image doesn't move. So what's going on is, what the VR does is that the world, the visual experience at least, and eventually other experiences too, they react to every little thing that is below cognitive level. Because most of the time we don't know that I moved my eye to the left or to the right. Most of the time I'm not aware where my eyes are going. But when I move my eyes, the visual scene doesn't move like that, even though that's what happened on my retina. That's what is happening with VR. And that's what this complicated dialogue between this is the result of my action, what my eyes are seeing, the room coming, the walls coming towards me is the result of my action. That's a complicated calculation. That's what we believe starts to get busted in these complex diseases. And that's what VR allows you to probe in a systematic way, because in VR, you can decouple them. So it's a good thing and a bad thing. And to get out of this, to answer the episodic memory question, I won't have time to show you slides, but I'm more than happy to share. What we did is that to generate a purely episodic memory, we just had the mouse sit somewhere, and on a giant surround screen, we played a movie, a human movie. It's a movie that's from 1950s, A Touch of Evil. And the neurons in hippocampus started to respond based on the plot that was evolving. So now that selectivity, we partnered with Allen Brain Institute. They did this study across all kinds of structure that I showed you, and we found no matter where we look, in visual cortex, LGN, hippocampal subregions, those neurons reliably encoded specific episodes of the memory. Visual cortical neurons responding to specific visual cues, hippocampal neurons were chunking those visual information and creating little bits of experience. So that's the episodic memory result, which somebody, if they're interested, they can look. It's just coming out in print next week.
Okay, so to sum it up, what virtual reality is doing, VR allows us to understand how neurons respond to different inputs, number one, and also it helps us articulate how to make mice act more human so that we can understand the human brains and the targets that we are exploring for drug therapies for Alzheimer's.
Exactly. And in addition, we find that the best way to do translation is not just to rely on self-report, either of human or of animal, but look inside the brain. Because whether the mouse improved or not, the improvement or lack thereof could be due to God knows how many reasons. When you look inside the brain and find out, now you have dozens of biomarkers. And what we found is that those dozen biomarkers in the brain in mice in virtual reality match perfectly with non-human primates, as well as a handful of human studies. So that's VR is an effective translational tool. And VR is able to do funny things to the brain. It's able to change brain rhythms. It's able to shut down the activity of neurons. So we need to potentially treat that as a very complex tool, not just something that we should be using willy-nilly. We should be careful and say, maybe this is good for me, but we don't know right now.
Right. And answering the question about how much neural activity is actually good for the brain and how much actually overactivity causes degeneration, right?
That's exactly right. So all that needs to be sorted out. And the one line summary will be that what VR does to the brain is completely different than watching TV does to the brain. And we must be cautious, optimistically cautious, and use this carefully. And what I would like to send out a message to whoever might be listening is partner with us so we can leverage this tool and avoid any potential side effects. We don't want that to happen. Then
So
it's
we're
good
not
for
ready to
everyone.
say to our 14-year-old kids who want an Oculus, we're not going to say yes right away because we don't know what this means for the brain.
Yeah, we're not going to say no, and we are not going to say yes. We are going to be cautious to say it's not the same thing as watching a big screen TV.
Yeah.
It is something else. It's reacting to our movement at a subconscious level. It's a new territory that our brain has entered, and it's an interesting territory. It's a powerful tool. Let's understand it before we take it for a ride.
I mean, we unleashed, we unleashed our phones to
That's
the
right.
world, and we don't actually know what they're doing to our brains, right? I mean,
And recently we have unleashed AI on the world, and now the governments are freaking out. Oh my God, will it be bad? This tool as well has been unleashed on the brain. Right now, God knows how many hundreds of millions of people are experiencing all kinds of VR every day. And
yeah.
my message is, I would like to find out what are the long-term consequences. Are they good? Are they bad? Or don't even think about it. It's just like watching TV. I
Well,
would like to find that out.
this is so fascinating. Thank you so much for sharing this. I'm fascinated in this space, and I do believe that we will learn a lot more through virtual reality and all, and implementing the latest technologies. Thank you, Dr. Mehta. I think we've posted links to your research in this talk, but keep us abreast of the results. I mean, I do hope we find out more through the mouse model, and I hope people do take you up on using this so that we can have more answers. But thanks so much for sharing your research with us.
Thank you. Great questions. Enjoyed the conversation. Happy to chat anytime.
Okay, and just to remind our audience and our community, Dr. Mehta is at UCLA and continues his research there, I believe.
Yes.
So we'll also post a link as to how people can get in touch. So thanks very much.
Absolutely.
Thanks
Thank
very much
you.
for your time. We look forward to talking to you again. And for those of you who might have missed some of this, go to beingpatient.com. Don't forget to sign up for our newsletter. That's when we let you know about talks like these, super interesting, from experts. So thanks very much for joining us, and we'll see you all next time.